Hello, my name is Valdez. I'm a professor at the Department of Mathematics at the University of Connecticut. And I'm very pleased to be here with Dr. Gao Nu, also from the same department. And we're here to talk about unlocking reserve assumptions based on the retrospective loss random variable. This is also joint work with our colleagues, Dr. Vadiveloo, who runs the Goldenson Center for Actuarial Research, and also Dr. Gan, also a member of the mathematics department. First, I want to talk about an outline of our work. So our work is basically based on calculating reserves, in particular life insurance reserves. And as we say in the first bullet here, we calculate reserve based on a prospective loss random variable, and we would calculate based on the mean, or also maybe something using other risk measures other than the mean. However, we've also shown the equivalence of this prospective reserve with a retrospective form. So prospective reserve is usually calculated based on looking forward, and hence the word perspective, whereas retrospective means looking backward. And we've shown the equivalence between these two reserves. However, we've never defined historically a random variable that would correspond to this retrospective form of the reserve. So our paper makes this major contribution by defining a retrospective random variable, and we showed that its expectation is actually the same as the expectation of this prospective loss random variable, so that in essence, the two are also equivalent. So this random variable, we also show in this paper, can be used as a powerful tool for providing us important information, in particular historical information on the pattern and significance of the deviation of your actual experience from that assumed for reserving purposes. So the purpose of this paper, and in fact most of our contribution for this paper, is that we can use this random variable as a guide whether it's needed to adjust your prospective reserves, and if you do need to adjust, how do you do the adjustment? So we also talk about the procedure for making such an adjustment. So the new law allows you to unlock assumptions. However, you have to justify it. So this is one major contribution of our paper, because it gives you a way of justifying whether you need to adjust your reserve based on your historical experience. So this is actually a part, in fact, a small part of a bigger project that we're doing at the Goldenson Center on claims tracking and monitoring. So for an illustration, we're going to consider what we call a fully discrete N-year term insurance policy issued to a person who is age X now with a death benefit of M. So we use the symbol M for the death benefit, but we also use the symbol P for the annual level premium. Now we are going to assume that the annual level premium is determined according to the equivalence principle. We'll expound that a bit more later on. But here we're talking about a fully discrete term policy, which means that the benefit is paid at the end of the year of death, and premiums are paid at the beginning of the year. Okay? So at policy duration T, so this is now number of years that have elapsed after policy issue, we're now interested in what we call the prospective loss random variable. And by definition, that's just the present value of all your future benefit minus the present value of all your future premiums. So that's why this is called prospective, because you're looking forward. Okay? So all the benefits that you have yet to pay minus all the future premiums that you have yet to receive. The difference between these is what we call our prospective loss. Now for policy, it's easy to show that formula up here where the present value of the future benefit is really your M, which is the amount that you do pay when you do die. And we also have the random variable K, but that K is based on the age at which you have reached at duration T, so which is x plus T. So Kx plus T is actually what we call the discrete future lifetime of a person who has reached x plus T. Now we constrain this to n minus t years because our policy only goes up to n years. Remember, it's a term insurance policy, so it has an expiry after n years. Now, the same thing for the future premium. The future premiums is an annuity that ends either at the end of n years or the time that you do die, if that happens to be before n years. So the prospective reserve then is easy to show. Based on the expectation is going to be the expected value of the present value of your future benefit minus the present value of your future premium. So these are just standard actuarial symbols for the expected present value of the future benefit. So that's an M multiplied by a big A. So a big A usually refers to a present value of an insurance policy, and then the A double dot denotes an annuity. In this case, it's a life annuity that starts at x plus t and going only up to n minus t years. Remember, we are looking at time t, so that person has reached age x plus t and you only have n minus t years left. Now, the equivalence principle says that at time of issue, this expected prospective loss is going to be 0, so that the present value or the expected present value of your future benefit at issue is equal to the present value of your future premium at issue. That's the equivalence principle. So now, using that result, a little straightforward algebraic manipulation will lead us to the following form of the retrospective reserve, which is the one here at the bottom here. So it's actually now, in essence, if you want to interpret this, this is the accumulated value of your past premiums minus the accumulated value of your past benefits. Now I think we're ready to define what we call the retrospective loss random variable. So again, recall the special case that we're looking at, which is an n-year term insurance policy issued to a person who is age x, and we denote the discrete future lifetime of this person by kx. So x being the age at issue and k being the number of years. In fact, this is the integral number of years that you have lived before you do die. So if kx is less than t, t is our policy duration. This is the time at which we're calculating the reserve. The policyholder either dies or is going to be alive. So if the policyholder dies before reaching age x plus t, we define the retrospective loss random variable to be the following. So you can see here from that formula up there, we start with P with the A double dot angle K x plus 1. So that means that's the present value of all the past premiums paid at time t, but accumulated to time t. Okay? And we minus the benefit that we would have paid for all those people who would have died. And that's where the 1 plus I raised to t minus kx minus 1 comes from. Now, the denominator is dividing by the portion of people who have survived to reach age x plus t, the time of valuation. So the first term above, like I said, is the accumulation at time t of all past premiums, and we minus that with the second term, which is the accumulation of all death benefit at time t. So here we interpret the retrospective loss random variable to be the realized gain at time t for each surviving policyholder. And that's why we're dividing it by TPX, which is the proportion of people who have reached to survive to time t, attributable to all those who died before the evaluation date. Now, however, if you die after the evaluation date, we denote we define the retrospective loss as the constant, which is simply the accumulation of all the premiums that you have paid. Recall, you are alive at time t, so there's no benefit paid, but these premiums are accumulated to time t. And again, the same thing as before, we divide this by TPX to calculate only this retrospective loss for each surviving policyholder. So in the previous slides, we defined our retrospective loss random variable based on the case when you are alive at duration t, or you are dead by the time we have reached duration t. So here we can express the retrospective loss random variable by combining those two much more succinctly as the expression up on the top here. Okay, so it's a little bit complicated, but it should be easy to interpret. One simply says that, so the only difference has to do with the benefit payment being paid only if you died before time t. There's no benefit payment paid if you do die after time t. So now we're ready to show that the expectation of this retrospective loss random variable is actually equal to the expectation of the prospective loss random variable. And that formulation is quite straightforward, just using formulas that we have learned from life insurance mathematics. Indeed, we can write the expected retrospective loss random variable as follows. So again, the interpretation here on the second formula is that you're accumulating all the past premiums and then minus the accumulation of all the past benefit that you would have paid. The denominator is simply accumulate, and a formula that is used to accumulate that amount. So using the actuarial equivalence principle, as I have said before, this is actually saying that the expected future premium at issue is going to be equal to the expected future benefit at issue. So that's what we call the actuarial equivalence principle. So using this formula, it is rather straightforward, and some of the details are actually in our paper, that the two expectations are indeed equivalent. So previously we have shown that the two expectations are equivalent. However, the two random variables are not equivalent. So here we show, for instance, the case when you start at duration 0, it's clear that our retrospective loss random variable will always be 0. However, for the prospective loss random variable, it's not the case. It's actually the present value of all your benefit yet to be paid minus the premiums that you still have to pay in the future. So that value is not necessarily 0 at time 0. In contrast, when we look at policy maturity, recall this is an n-year term insurance, so the prospective loss random variable would be equal to 0 because you don't have any more benefit to pay, you don't have any more premiums to pay. So, however, if you look at the retrospective loss random variable at policy maturity, it will be equal to this term here on the bottom, which is not always going to be equal to 0. So very clearly, just looking at these two extreme durations, the two values are not equivalent. So clearly there is a difference between the two random variables that we have defined. In effect, if you want to interpret this difference, the prospective loss random variable can be viewed as the share per survivor of the present value of your net liability for every dollar of insurance at duration T. On the other hand, the retrospective loss random variable can be interpreted as the share per survivor of the accumulated net assets for every dollar of insurance at duration T. In the previous slides, we have seen the difference between these two loss random variables. Here we show graphically again the difference between these two based on the realized prospective and retrospective loss at duration 10. Here we're looking at a very specific term insurance policy, one with a term of 25 years. So the left-hand side is the realized prospective loss, and the right-hand side is the realized retrospective loss. Now note that one difference between these two loss random variables also has to do with how we calculated the loss random variable. One, in particular the prospective loss random variable, is based on the age at x plus 10. We're looking at duration 10, so we're looking at the future lifetime of this person at that point in time. Whereas when we look at retrospectively, we're looking at the loss random variable of the person from issue. Okay, so interpreting these graphs here essentially says that the left-hand side, you have large realized prospective loss when you do die before 15 years, because we have 15 more years remaining, and then it becomes constant after that. That constant is actually a negative loss, which is a gain, which is a reflection in some sense of the retrospective loss, because remember, the prospective loss is a net loss, whereas the retrospective loss is actually a net gain. So here, if you do die before 10 years, we have a large negative loss, which is a large gain, but then you do have a lot of losses if you die before time T. So this is another way of looking at the difference between the realized prospective and retrospective loss at duration 10. We're looking at the same 25-year term policy. Here we note that we do have a large probability of having a negative loss prospectively at time T equals 10. And this is quite the opposite of the retrospective loss. So this simply shows you the distribution between these two loss random variables. As you can see, a big difference, a large negative loss for prospective and a large positive loss on the retrospective side. So here's another way of looking at the difference between the retrospective loss and the prospective loss random variables. Here we're looking at a table of means and standard deviations. There's a few observations that we can make here. One is that the mean, as you can see, both between the retrospective loss and the prospective loss are always the same for each policy duration. We're looking at here only a 20-year term policy. As you can see at the bottom here, when you reach 20, your reserve would have been 0. However, note the difference in the standard deviation. As we have shown before, the two distributions are very much different. There's also a big difference on the standard deviations. One observation you can make is actually at early durations for the retrospective loss, the standard deviations are small, but they increase over time. And this is quite the opposite of the prospective loss. It's quite large in some sense in the beginning and then decreases over time. Now another observation that we can make is on the amount of the reserve itself. It starts small and then increases over time because this is a term insurance policy, and then at some point it starts to decrease until it reaches 0 at policy maturity. For this case, we're looking at the life insurance coverage of 1,000 and a policy issue at age 45. Again, I said 20-year term policy, and we assume this was issued to a male, and the interest rate that we assumed here is 5%. We can extend our definition of retrospective loss random variable to any form of insurance. So for example, in the fully continuous case, so this is the case where the benefit is paid immediately upon death, and the premium is also continuously paid. So we use here the benefit amount, the same notation as we have before, the big M, but the premiums are now fully continuous, so we use P with a bar on top, which is quite a standard symbol. So the top formula up here is the retrospective form of the reserve at time t, and the next equation is actually the prospective loss at time t. So the top one essentially has the same interpretation as before. We accumulate all premiums paid to time t, and we deduct all benefit paid to time t. Note that there's an indicator there that you only pay benefit for those people who have died before duration t. There is no benefit paid if you have survived to reach time t. So just like the discrete case, if we use the equivalence principle, so this is this equation here, which says the present value of all future premiums is going to be equal to the present value of all future benefit. So if you use that equation, it's straightforward to show, in fact the details are again in our paper, that the two expectation, the expected retrospective loss random variable is going to be the expected value of the prospective loss random variable.
Hello. Next, I would like to go through some numerical examples and some reserving practices based on retrospective loss random variables we have defined. Assuming you have a 100 insurance policy portfolio, and all of them are 20-year term insurance, and the face amount $100,000, interest rate 5%, and they're all 45-year male. Now, based on appropriate mortality assumption, you should be able to calculate the mean and standard deviation and a variety of quantiles of this retrospective loss random variable. After we calculated the mean and the standard deviation of retrospective loss random variable, we can plot them into this kind of confidence band types of graph. As you can see, as the duration goes up, the mean of this retrospective loss random variable is kind of going up then down. But the standard deviation is constantly increasing. Now, what that means is at different duration, the retrospective loss random variable will providing us different amount of information. Now, the next slide I want to show is how are we going to use this information so that we can unlock our reserve in a theoretical correct way. Next, I would like to talk about the implications of retrospective loss random variable. The realized retrospective loss random variable, it represents the historical claims experience, which is what actually happened. Now, if there is a significant deviation of the realized retrospective loss random variable from the assumed or expected retrospective loss random variable, then that could indicate the assumptions are not accurately reflect the experience, which indicates the prospective reserve should be adjusted. The definition of significant deviation and the level of adjustment of a prospective reserve, we could use some GLM confidence band approach, which is done in a separate work. Now, a credibility adjustment could be created by having the confidence interval vary by reserve duration, which means at different duration, the band will be different, the adjustment will be different, because as you can see from the previous slides, at a different duration level, actually the retrospective loss random variable provides you different amount of information. Now, the later duration policies, we should have a tighter confidence interval since there is more historical experience available. Next, we're defining a credibility adjusted confidence interval. The overall consistency requirements is that we want the later policy durations, it has a tighter confidence interval. Because the later duration policy have actually more credible historical experience information collected. Now, if we define the confidence interval with the width as 50% of upper minus the lower bound, and that value will be our confidence interval. Now, if we keep the confidence width fixed for all duration, which will lead to a tighter confidence interval because as the duration increases, because the standard deviation of the retrospective reserve increases by duration. In the end, we will end up with a linearly decline the confidence wins to 0 from duration 1 to the end of coverage period. Next, we'll go through an application of how do you utilize this retrospective loss random variable help you to adjust the future reserves. For example, let's have a hypothetical in-force block of 20-year fully discrete term insurance policies. It's issued over the past 10 years. Every year, there are 100 policies are issued, and they are randomly issued over the issue ages of 35 to 55 years old people, and also the face amount is from $100,000 to $500,000, and the premium are based on the equivalence principle. Now assume for the duration 1 to 5, which is the policies issued the most recent years, they have actual historical mortality, or the experience mortality is assumed to 25% lower than the reserving assumptions. And also another block of business, which is the duration 6 to 10, which is the much earlier issues, assume their actual historical mortality is to be 25% higher than the reserving assumptions. Now we want to show that with this particular method, are we be able to test out of this 25% lower and the 25% higher? Our method of adjustment is the prospective reserves will be adjusted based on the deviation of realized retrospective loss random variable from the confidence interval we created based on the retrospective loss random variable's mean and the standard deviation. Now assuming this confidence interval is based on 10% standard deviation for the policies in duration 10, and linearly goes to 100% standard deviation, which is 1 standard deviation for policies in duration 1. Is because in duration 10 we have more historical experience, we want to have a tighter confidence band. Now assuming there is only one decrement, that is mortality, and the prospective reserve is being calculated at the end of duration 10. This graph shows the exact process of how do we adjust the prospective reserve. Well, there are 3 keywords. Number 1 is expected prospective loss, then there's adjusted prospective loss, and there's a realized prospective loss. The expected prospective loss is based on the assumption of the VPT table or whatever the mortality table assumed. The adjusted one is based on our confidence band. Now what we want to show is whether this adjusted one is similar or close to the realized one, which is 25% higher or lower for each different of the block of business. Now how do we do this adjustment? We are able to calculate the realized retrospective loss random variable, that is the 13%. Now we will compare this, the realized one, with the confidence interval we have defined to see whether it's within the band or it's upper or lower bound. Now if the realized retrospective mean is fell within the confidence band, then we will just assuming this will be normal fluctuation, there's nothing we need to be changed. Now if this realized one is above the bound or the lower the band, we will adjust it accordingly. Actually, it's reflective. If the realized one is above the retrospective, the confidence band, we'll adjust it down. And if it's below, we'll adjust it up. Therefore, we are able to end up with adjusted prospective loss mean, which is the reserve we're thinking need to be adjusted to. In the previous slides, we talked about how did we perform this adjustment to the prospective reserve. Now in this slide, I want to show some of the results. The remaining policies, it will not from the beginning 1,000 drop to 993 policies now. There are 3 concepts. It's expected reserve and adjusted reserve and realized reserve. And also there's the prospectively and the retrospectively. Now as you can see, the expected retrospective reserve is equal to the expected prospective reserve on the 3rd row and the 4th row. It's because life contingency actually already showed that the equivalence between the retrospective reserving and the prospective reserving. However, it won't necessarily realize the change or the difference between your assumption and what actually happens. So the realized retrospective reserve is $11.04 and actually a little bit higher than the assumption. That's because there are 25% higher and 25% lower mortalities compared with what you assumed with your mortality. And according to our adjustment process, what we're recommending here is $11.11 for the adjusted prospective reserve, which is actually a little bit higher than the realized prospective reserve, and in the sense that it is more conservative because we're encouraging for a higher reserve. Now, this graph really shows a per $1,000 basis as well as the aggregate basis. And it is actually closer. The adjusted prospective reserve is closer to a realized prospective reserve compared with you do not unlock your reserve assumption, just to use your expected value. Next, the process of adjusting prospective reserve in practice is breaking down into this process. First, you need to break up the in-force block by the plan of insurance. It could be term insurance, whole life insurance, different term insurance. Then for a given plan of insurance, you want to break up the policies by different duration. And for each given duration, you want to determine the number of policies issued in the very beginning. Then you can calculate the realized retrospective reserve at the date of duration. Then you can compare against the retrospective random variable confidence interval for that particular duration, and you can determine what is your adjusted prospective reserve going to be. Then after you adjusted for each duration, each plan of insurance, then you can calculate the total adjusted prospective reserve for that particular duration and the total portfolio. Then you can repeat all these for the all different plans of insurance, and those will be the adjustment process for the whole portfolio. In the end, I want to thank my colleagues, Dr. Vadiveloo, Dr. Valdez, and Dr. Gunn for their excellent work. Hopefully, industry can benefit from this adjusting prospective reserve or unlocking your reserve assumption. Hopefully, you are able to get an accurate reserve practice. Now, this research is a part of applied research work undertaken by Golden Center for Actuarial Research at the University of Connecticut. We strive to deliver research work with implementable solutions based on real-life issues faced by industry by using faculty members and graduate students in collaboration with industry professionals. Thank you for your watch.